My plan was to get much farther before we started. I didn't realize that you were going to have trouble with what we did yesterday. So no big deal though. I hope that by now you feel a little bit better about sketching cells, what's going into those things, what it means to have standard conditions, and how to draw line notation. That was worth spending time in class, but we need to move along a little bit. And the next thing that we're going to be hitting, I said the S word the other day in class. Remember that S word? Spontaneous, yes. And that means that we revisit our old friend, Gibbs, our old friend Gibbs. Yep. Now, I'm just going to do this on the board. Let's do a little derivation. It's fun.
Not today.
That's not
Okay. He's our old friend from earlier in the year. Yes, you know he's our friend.
He went to our class one time. Hung out with him for a whole chapter. I didn't say anything.
A couple of days ago, when introducing cell potential difference and electromotive force and voltage, I told you that the definition of a volt is a joule per coulomb. Now that doesn't mean a whole lot because we don't really know what a coulomb is. We know what joules are. Joules measure what? Work or energy. Right. Now I said work up here. It's the same thing as energy though. Don't we need energy to be able to do work?
Amen.
Our amount of work is limited by the amount of energy we have. That's what Gibbs free energy is. Gibbs free energy tells us how much energy we have available for doing work. That is what happens in a cell. Current is traveling through a wire. That current is a form of energy that can do work. Volts are how much energy we have per charge that's flowing. The symbol Q is used to symbolize charge. Now we've already used a Q earlier in the year that's not the same Q. It's the same letter. What Q did we use earlier in the year? Q equals MC delta T. And capital Q for equilibrium, right? Reaction quotient. But lowercase q is for heat. Don't be confused because it's the same letter used for a different quantity. Spencer, let's move that shade down just a little bit. Let's make a definition of charge. Charge is very difficult to define. I find it to be a nebulous concept. I can't really give a good, clean definition of it. Charge represents what? Positive or negative? People in physics? What's charge?
How do you charge?
Anybody in AP physics?
I'm not in a real physics. I'm in physics 1.
Yeah, me too.
Okay. So charge is, it's very difficult to charge. An electron has a certain charge to it. So rather than giving a nice clean definition of what charge is, here's what I can tell you. A mole of electrons, for instance, if you have a mole of silver and every atom gives off an electron, which they do, you'd have a mole of electrons. That would have a charge that was developed by a guy named Michael Faraday, 96,485 coulombs of charge. So that's our definition of charge, is that a mole of electrons has that many coulombs.
What is a coulomb?
It's a measure of charge.
That's
That's what I'm talking about, E-Man. And that's exactly what I mean by, man, it's hard to define what charge is. I can't do it, honestly.
You're going to have fun watching this video.
Sorry, Drew, it's Friday.
I have people.
All right. Now, I will tell you that this conversion factor right here is known as Faraday's constant. 96,485 coulombs. That is what is the charge of 1 mole of electrons. Now, what if you don't have a mole of electrons? What if you have a half a mole of electrons? Then you'll have a half this number for your charge, right? Spencer, let's move down a little bit. So I'm going to redefine Q and stop. Q is defined as the number of moles of electrons times F, which is that number. So this relationship means, just what I mentioned a minute ago, if you have a half of a mole of electrons, then your charge would be half of that number. So you just take 0.5 times that number, that would be the charge.
We have to memorize the charge.
Yep, 96,485. If you called it 96,000, I'd be thrilled.
Sounds like a.
No, it would be
If
490.
you can't remember it, then don't worry about it. That will be given to you on the AP exam, I think, but not on the quiz. So if you need it on the quiz, you ought to know it. All right.
9.
So where I gave this definition, work over charge, I'm going to just replace it. I did that over here as work over number of moles of electrons times F. Now, what is W? Work, right? Is work the same thing as energy? Mathematically, it is, because you can't do work without energy. So work is limited by the amount of energy you have. What symbol do we use for energy?
Absolutely.
No,
Delta E.
Delta G. We're talking about Gibbs, right? The free energy, which is delta G, is the amount of energy that's available for doing your work. That's why they call it free energy. In some process, like the electrons flowing through a system, that flow of electrons is able to do some work, and so that's limited by the free energy that's available. All right. One other thing, though, and that's the sign convention. You remember that when a system does work on the surroundings, what's the sign on W?
Negative.
It's negative because it's losing energy. Yes? So really, this thing means negative delta G over NF. Yeah, and that's, if we rearrange this thing, I want you to write this down too. Delta G equals negative NF epsilon. Taking a look at signs, what's the sign on N? Ignoring that negative sign, just the sign on N. It's number of moles of electrons, so it's going to be a positive number. F is a constant, it's always a positive number. What about E? The epsilon. It can be positive or negative. If it's positive, if this number is positive, what can you say about delta G?
Negative.
Delta G will be negative. That's why you need a positive cell potential to have a spontaneous reaction. Now, delta G turns out to be a pretty big deal. I warned you about this earlier in the year. We have 3 different ways of finding delta G. If you know enthalpy and entropy, then you can find delta G. If you know an equilibrium constant, you can find delta G. And that tells you if K is greater than 1, this whole term is going to be negative, and that makes delta G negative. Well, no, it makes delta G negative, which means it's spontaneous.
Wait, no, if ln of K
If ln of K is greater than 1,
is great.
then that whole side is negative, because that's positive and that's positive, and that's positive too. That whole side will be negative. And if the cell potential is positive, then delta G is negative. So we have many different ways of telling whether a reaction will be spontaneous. We can use the cell potential, we can use the thermodynamic data, or we can use the equilibrium data. Spencer, let's go to one last slide. Nope. The last slide is going to be how much work can be obtained from the galvanic cell described by this reaction. I found in first and second hour, I got to this slide, I was not able to finish either one, and now we're going to have 2 days off. Let's not even bother starting.
Okay.
Part of the problem is you don't have ClO2 negative on your reduction potential table. We have to go to the Zumdahl book. So let's do that. I'll probably just copy new reduction potential tables for you. Let's just call it good for today.
Yay!
Yep. Thank you, Eric. I'll hang on to it.